All right, welcome back to the NMR discussion. Now we are ready to move on to the carbon NMR. As you know, carbon regular isotope 12 has those quarks, canceling up their spins. So overall, because the atomic number and atomic weight, they're even numbers, the carbon 12 is inactive. So about 1% of the natural abundance for carbon 13 is there, and that has a half spin. Therefore, we can use rare carbon 13 isotopes. We can still detect the carbon backbone using isotope of 13. Yeah, so like I opened up the discussion, carbon 13 has faced some challenges. Number one, like I said, 1% of the natural abundance for only active one, carbon 13. Therefore, relatively, you need high concentration of sample. And if you're gonna use the same sample you made for the proton NMR, the signal and the noise ratio is quite poor, so you will notice quite noisy baseline for the carbon 13. Also, due to the size of the carbon, the gyromagnetic ratio is somewhat less. It's about 1/5 times of hydrogen. Therefore, you also need to have more concentration. Additionally, you may have to run more experiment, longer time with more scan. Also, hydrogen on each carbon, they actually couple. Hydrogens actually couple with carbon nuclei. Nuclei, excuse me. And the couplings around, roughly speaking, 100 to 300 hertz, and that's relatively big number for the splitting. Okay, remember the coupling gives splitting. Splittings for hydrogens are, among the hydrogens, are normally about less than 10, or sometimes a little more than 10. But as you can see, it's about 10 times greater splittings you get. And each carbon has multiple hydrogens, so you expect the splitting makes the carbon 13 NMR quite complex. And good news is we overcame this issue using the pulse technology. Okay, so the pulse technology that I'm gonna probably talk about with the video for a major student. Using pulse technology, we can actually decouple decouple the hydrogen. So you can only observe carbon 13, not 12, carbon 13's signal. And thank God, you have a low probability of finding carbon 13 on the chain. So you usually, with a small molecule, you happen to have one carbon 13 in one molecule. So there wouldn't be any coupling between carbon 13s. So if you imagine ethanol molecule, you have a mole of ethanol there. Among the moles of the ethanol molecules, about 1% of the carbon will be active. So there are only 2 carbons here, so chances to have carbon 13 here is when you have a 50 molecules like this, only 1 carbon here out of the whole 50 molecule will have an active carbon. So that's the case. So some of the molecules don't even have a carbon 13 in it. That's why we need high concentration sample, but thanks to that, we don't have to worry about decoupling between carbons. So these are the challenges to do carbon 13 experiment. But reading spectrum became easier due to some technological assistance. And if you remember, hydrogen NMR gave us 4 different informations. But on carbon 13, you don't need to worry about integration, neither about coupling. Also for HNMR, when you have chiral center, you have to worry about the enantiomers or diastromers giving different type of signals. And even for this type of two hydrogens next door, it doesn't have to be next door, but in the molecule, if you have hydrogen that's not really on the chiral carbon, but due to the chiral environment here, this hydrogen feeling different charge, meaning different magnetic local magnetic field compared to the other that is closer to the hydrogen, not OH, right? So the magnetically they're not identical, so they're not homotopic anymore. And they're not even enantiotopic. But actually they are diastereotopic. Hydrogens, so they will have different chemical shift. They will have a different couplings. So the 2 signal will be shown for these 2. And this will be discussed in the video for majors as well. But the point here is that even for the non-major, you need to know the carbon 13 is much simpler because you don't even have to worry about these stereochemical issue. Only thing you have to figure out is how many types of carbons you have and where they appear. And in order to find out number of signal, you apply symmetry, mirror rotation technique to match up. Then that's about it. All right, first, the locations. Unlike the proton NMR, you have 0 ppm to 200 ppm, roughly 20 times, right? roughly speaking. So the sp3 carbons, this time it's not hydrogen, right? Those are the carbons that you are trying to detect. Our first block, 0 to 40. It was 0 to 4, but now it's about 10 times. 0 to 40. They can easily go over. Depends on what you have, but roughly speaking, right? We don't totally rely on exact number of ppm, as you know. So that, and instead of 2 to 1, roughly 20 or less for the normal alkane with a no electronegative atom nearby. That carbon shows up here. Then sp carbon hydrogen was about 3 ppm, but it's now here around 80. Then the triple bonded carbon to the nitrogen with electronegativity, right? It comes around 100 something to 120. Then you remember the order. Regular alkene carbon comes in. It was a 4 to 6, but here 120 to 140. And then the benzene aromatic carbons, it can come from in the middle of this area somewhere, like 130, 120 something is possible too. Go to the 160, but it could go over 160, depends on what you have. You should apply resonance and the inductive to deduce the changes, right? Then the carbonyls. Remember the aldehyde hydrogen was there around 10-ish. So roughly 20 times, around 200-ish. You have all kinds of carbonyl carbons, these carbons. Okay, you expect them to show up here. And if you have carbon and hydrogen, ketone and aldehyde, they are more likely to have a greater number than 180. And those esters and the amide likely to have a smaller number than 180. But again, I'm not gonna strictly go by that if you're non-major. So carbonyl carbon around here is enough, okay? So really, roughly speaking, around 40-50 sp3, closer to 40-50, you get electronegative atom, okay? After that, you have triple bond up to 120. Then double bond up to 160. Then the higher half is aromatic, lower half is alkene, not so strictly though. Then carbonyl, something like 170-ish to 200. That's enough. So once you recognize this and memorize, you will just have to come up with how many signals you have in the molecule, and then you can connect the functional groups to these, and then you're all set. Okay then, how many signals of carbon-13 CNMR you expect? There's no symmetry whatsoever, right? So 1, 2, 3, 4, 5. So you expect 5 signals. Which area you are looking for? If you remember, it's from 0 to about 50, right? Oh my gosh. In reality though, you can get the number around 0 to 60 even. So the close to the oxygen, these two can show you a signal, one here, one there. And you can guess which one gives even more frequency. Remember, these two are compared and the neighbors have 3 hydrogens on this carbon. The neighbor has 2 hydrogens on this carbon. So this carbon is more shielded. Therefore, this should be also more shielded. So if I label A, B, C, D, and the E, you'll see this signal is a B, that signal is the C, right? And then the following one, right? This one has a oxygen in the beta. So roughly speaking, like I said, about half. So about 50, 60. So if this was a 30, right? Somewhere around here, you expect A. Then where do you expect D? And that one's next to CH2, right? And it has a carbon as a neighbor, not 3 hydrogen on it. So it's a little more D-shielded, so closer to this. This has to be your D. Then E is far away from oxygen, so more shielded. So expecting signal around here, that's E. Okay. By the way, this is the NMR of carbon-13 that's decoupled, okay? You decoupled hydrogen, so you get only one line for each carbon that are different. So how many signals on this compound do you expect for carbon-13? If you apply the symmetry operation, you have 1, 2, 3, 4, 5, and there 6, right? So let's label them out. Here they're same if you apply a mirror. Then the chemical shift. Since you figured out the number of signal, only thing you have to do is a chemical shift, because we don't have to worry about splittings and integration. Let's first go to the carbon here. Carbonyl carbon, which is an ester. Remember that was around what? Little less than 180, but around 180. So you expect a signal for C right there. Then what else is more de-shielded? Is it the B or D? B is actually beta, not alpha to the oxygen, right? Beta to the oxygen. Even when you have 2 of them, the D, which is alpha to the oxygen, is more de-shielded. So D comes next as alpha. But one of the most de-shielded sp3 is close to the 50-60, right? So I'm gonna give, to be safe, 60 here. A signal for D. Then what else? There are some betas now, right? So the CH2 here and the CH3 is there, which is more de-shielded, you think. They have more hydrogen numbers, and also they are in the beta to 1 oxygen, but this B has 2 oxygen in the B location, and that has only 2 H's giving electron to the carbon. So that should be the next one coming. We cannot tell exactly again, but let's say about half, right? 30 for B. Then close to that, you have 2 E's. I mean, the integration is not there, but usually they're somewhat taller. Not necessarily twice, but somewhat taller. We don't really rely on that, but you can get some hint like that. Then you have the gamma from the oxygen. The carbon there, A, is giving small number. 8, you know, something around 10-ish. So that should be about 20 something. So that's how you do. Later, we'll do more in detail, but there is an experiment called DEPT. We are using special pulse, series of pulse to run carbon-13, still decoupling the hydrogens. With a pulse of 0, 45, 90, and 135 degrees, you get these kinds of outcome. As you can see, those experiments with some degree of pulse, you don't see quaternary carbon, the carbonyl carbon, the one without hydrogen, okay? But at 45, you see everything. That's how you figure out, oh, this thing is quaternary. That's how you figure out. Then you get the outcome from the 90-degree pulse. There, only thing you see is D, which is a CH. So only CH gives signal. Okay, so that's the key thing. 45 gives you a chance to find quaternary. Here, this gives you a chance to find, you can see, kind of tertiary, right? With a 1 hydrogen. Quaternary, kind of tertiary. Then there, with a 135 degree of pulse, only thing that's showing negative value, as you can see, is B, which is a CH2. Okay, so that gives you a chance to find CH2. So you find the C here, quaternary. You find the CH here with a 90. You find the CH2 here as a negative value, 135. Okay, no signal, one positive, only positive, and only negative. Okay, no, positive, negative, C, CH, CH2. Please remember that. And this becomes more and more important for sophomore organic chemistry carbon NMR. And I think this is all you need to know about carbon-13. I'll put up more exercise on the next video. Then I'll move on to the NMR lectures for majors. So have a good day.